So let's look at the following example that deals with corrective lenses and farsightedness, also known as hyperopia. So as a person ages, their near point increases. Recall that the near point of a person or the near point of an eye is simply the minimum distance that an object can be placed relative to the eye so that the eye still focuses in on the object and the person is able to see the object clearly. So the normal near point is about 25 centimeters. As the person ages, this value increases. So to temporarily restore the near point, a person can wear corrective lenses, also known as glasses. So consider a person whose near point has reached 80 centimeters. So it has increased from 25 centimeters, the normal value, to 80 centimeters. Suppose this person wants to read a book held 30 centimeters from their eyes. Assume the distance between the corrective lens and the cornea is 2 centimeters. In part A, should the person wear convex or concave corrective lenses? In part B, what exactly is the focal length of such a pair of corrective lenses? And in part C, what is the power of these glasses? So, let's begin with part A. So how do we know whether or not the person should use convex or concave corrective lenses? So let's begin by recalling what farsightedness is. So farsightedness, also known as hyperopia, is essentially the inability to see objects that are close to the eye. So that is known as hyperopia. Now, what exactly happens in hyperopia? So, let's suppose we have the following eye, we have the lens, and we have the cornea of the eye. Let's suppose we take an object as shown by the dot and we place the object a certain close distance to the eye. So the rays of light will bounce off from the object, eventually will reach the cornea and the lens and will refract. However, because of this condition known as farsightedness, also known as hyperopia, what happens is the rays of light are not able to bend quickly enough, and so the image is formed at a point behind our retina. Now, what exactly takes place within a normal eye? So within a normal eye, these rays of light are bent so that they converge at a point that is found on the retina of the eye, right on this position. But in such a condition, the image is formed behind the retina so that the object, the person, cannot focus in on the object and the object is not seen clearly. So, what exactly do we have to do? So we can use a convex lens as shown in the following diagram. So because our rays of light are not able to converge quickly enough, if we use a convex or a converging lens, that lens will essentially bend our rays of light even more so that this point is brought to our point that exists on the retina in the back of the eye, and now the person is able to see that object clearly. So, in farsightedness or hyperopia, the focal point is found behind the retina because the rays of light do not bend enough. To increase the convergence of these rays of light, a convex lens must be used. So notice that the lens found inside the eye is also a convex lens. So we essentially have a system of two convex lenses. So we're combining these two convex lenses. And such a system will essentially form an image that is found directly on the retina so that the eye will be able to see objects clearly when the objects are placed close next to our eye. So now let's move on to part B. So we know that the lens is in fact a convex lens, so the focal point, the focal length, should in fact be positive. So let's move on to part B. What exactly is the focal length of such a corrective lens? So let's once again try to understand what exactly is taking place when we're putting on our convex glasses, convex corrective lenses. So when we place our glasses, what happens is these glasses form an image of the object at the near point of that eye. And so the lens is now able to take that object and form an image of that object exactly on the retina. So to find the focal length of such a corrective lens, we have to apply the thin lens equation. So 1 divided by the focal length of these glasses, of these corrective lenses, is equal to 1 divided by the object distance plus 1 divided by our image distance. So given by DI. Now, what exactly is DO and what exactly is DI? Now notice we know we're given the fact that the distance between the lens of the glasses and the cornea or the lens of our eye is approximately 2.0 centimeters. So we're given that the person wants to read the book 30 centimeters from the cornea of the eye. So that means the distance from the corrective lens to where the book is placed is not 30, but 30 minus 2 or 28. So the object distance, the location of our book with respect to our lens of the corrective lens of the glasses is 28 centimeters, and it's positive because it's found on the same side as where the light originates. Now, what about our image distance? Well, if the person is to see that book, that means that the image should be formed at the near point of the person, which is given to be 80 centimeters. Now, 80 centimeters is relative to the cornea of the eye. Once again, we have this distance of 2 centimeters. So 80 minus 2 gives us a value of 78 centimeters. So that means this corrective lens has to form an image of the object 78 centimeters away to the left of this corrective lens. Now, because our image is formed on the same side as where the light originates on the left side, the image is negative. So the image distance is negative. So 1 divided by the focal length is equal to 1 divided by 28 centimeters plus 1 divided by negative 78 centimeters. We add and we solve for the focal length, and the focal length is equal to positive 43.7 centimeters. So this is the focal length of our lens, and it's positive, so that means it's in fact a convex or converging lens. And finally, let's move on to part C. What is the power of these corrective lenses, of these glasses? Well, the relationship between power and focal length is given by this formula. The power is equal to 1 divided by the focal length, given in meters. Now, we know from part B that the focal length is equal to 43.7 centimeters. So we divide by 100 to convert from centimeters to meters. So we have 1 divided by 0.437 meters, and that gives us a power of about positive 2.29 meters to the negative 1. So the positive means we're using a convex corrective lens.